Hi all, welcome to our YouTube channel Math Universe with Dr. Naseer Ahmed. Today we are going to take chapter probability of first year PUC. Okay, so let us mention that chapter name probability, and this, let us be very clear, it is for first PUC students because this chapter is again there in second PUC. So please be careful. And in total, you can expect 7 plus marks. In all the model paper, we can see 1 marker question, then one 2 marker question, and one 5 marker question. So it is 8. So 7 plus. Okay. Now before, as usual, going to the problems, first we are going to go for the concept. Now directly in the textbook it has started with events, but let us first try to go ahead with sample space, then types events and types of events, then we will come to the definition of probability. Okay, now is it visible? Fine. Now let us try to understand some of the basic concept. First comes sample space. Don't be shocked, etc. Sir, in textbook sample space is not there and you're starting with sample space. This is the base. Without that, we cannot go ahead. Our entire probability depends on sample space. Now, what is sample space? Sample space is defined as it is all possible outcomes of a random experiment. Let us try to understand what this statement is saying. It is all possible outcomes or nothing but the occurrence of a random experiment. Now, what is the meaning of random experiment? Any experiment satisfying two conditions. First, let us understand what is the meaning of the word random experiment. Any experiment satisfying two conditions. Condition number one, there should be more than one outcome. There should be more than one outcome. The output of the given experiment we call as outcome. Okay, whatever the result we get. So there should be more than one outcome. Do we have any example? Yes, real world problem. For example, tossing of a coin. When we toss of a coin, we have got two outputs. Which are those? Head or tail. The word or is important. Don't say head and tail. If you are saying head and tail, when you are tossing a coin, it means you are getting head also and tail also together. Okay. Now some people will say, no, sir, what if the coin is going to stand like this vertical? We are not talking about those cases. We're not talking about those fancy cases. We're talking about biased one, the realistic one. Okay. I mean to say unbiased one, not biased. Biased is partiality. Okay. So coming to toss of a coin, similarly, if we take rolling of a die, we have got 6 outcomes. So we have got more than one outcome in both the cases. So that's the example for this, and this 2 comes under random experiment because we have got more than one outcome. Second point is in advance we should not be able to predict the outcome. To predict the outcome. Understand this point carefully. Whatever, for example, tossing of a coin. In cricket, no, when, as usual, when they go for playing, first they have to toss the coin to decide whether they want to go for bowling or batting. So the captains of respective team will be on the field. One of the captain is going to toss the coin. The other captain, what he will do? He is going to guess the outcome. Is it head or tail? He is not going to predict. Predict, when I say, it should be exactly the same. But he's going to guess. Sometime true, sometime false. That's what we are saying. In advance, we should not be able to predict the outcome. Best example is cricket. Similarly, coming to die also, we have got 6 outcomes. First condition is satisfied. Second condition, when I am going to roll the die, we don't know either 1, 2, 3, 4, 5 or 6. Any one of them will occur, but which one exactly, we don't know. Sometimes it may be true, sometimes it may be false. Same like in cricket, no. Sometimes the toss is won by the captain and sometimes it is lost by the captain. Okay. Now let us come back to the definition. Definition: it is all possible outcomes of a random experiment, nothing but such an experiment in which there should be more than one outcome, and in advance we should not be able to predict the outcome. Did I just check? Is it recording? Yes. And the sample space is denoted by capital letter S. No small letters. Same like no chapter sets. The best way to understand this chapter is probability to try to relate with the chapter sets. There we had universal set, correct? Where all the sets are what? Subset. In place of universal set, we have got the sample space. Right, bit more bigger, yes. You may think as small letter. So the role of universal set is taken care by whom? Sample space. Now, what are the elements of called? First, let us try to take one example. Question from my end. Let us suppose, no, one question. Suppose 2 coins are tossed. Then what could be the sample space? Okay, then sample space. Okay, we have to find. Let us suppose then sample space is. Then sample space is. Let us suppose this is a question. Solution. When I have got 2 coins and I want to toss, see carefully. In right hand I got 1 coin, other hand I have got. So okay, so I mean to say right hand 1 coin, left hand other coin. So when I'm going to toss, it may happen that both are giving head. So sample space, both are giving head. It can happen that in the right hand when I toss I got head. Second means left hand I got tail. Nothing but head, tail. The other way around, it can happen that right hand when I toss I got tail and left hand I got what? Head. And lastly, both can be tail. That's it. No other possibilities. This is the sample space, and same like chapter 6, we are going to enclose the elements by flower bracket and equal to always capital letter S. Now, this elements, whichever is written here, we call sample points. Now, what is sample points? All the elements of sample space. How many sample points we have got here? 4 sample points. Correct? 4 sample points. 4 sample points. Or I can say this is a count. For example, number of element in sample space. How many are there? 4. So 4 sample points we have got. This part is the basic. Now we can go for the actual concept. But make sure you understand these things very clearly. Okay? Make a note of it. Okay. Dear students, having understood the basic, that is sample space and sample points, now time for the next concept, that is events. Now what is events? As I said, the best way to understand this chapter will be compared with chapter sets. There we had subset. Similarly here, what are events? Any subset of sample space. So the symbol for subset, don't forget this. And since for sample space the letter is capital S, and there it is universal set capital U in chapter 6, there we have subsets and it is denoted by capital letter A to Z, except the letter U is not used because for universal set it is used. Similarly here, coming to events, we can use any letter A to Z, but except yes, it should not be used. It should not be used. Okay, because this is only for sample space. So any subset of sample space, when can be equal? Nothing but I can have an experiment where all the outcomes will be same as the sample space. Now let us try to understand with the help of a example. Help of an example. So let us suppose now question tossing of it. Tossing of a coin. Okay. There is no need to say once. When I said tossing of a coin, it's understood only once. And this is the question. Let us suppose that in this event E is getting head. Getting head. Let us try to also take some more. No. Let us suppose one more event is the F, and I want getting what? 7. One more event. Getting head or tail. Let us try to go for solution of this. So here, tossing of a coin. Since I said a coin, the sample space can have either head or tail, anyone. Where H stands for head and T stands for tail. Now, how well you are reading the question, understanding is important here. Here, no, we don't have too many formulas. Logically thinking, understanding the language given to you is very important. Now you see, they said getting head. First, come to sample space. Whatever they're asking, is it there the sample space compared? Head. Yes, head is there. So, E is equal to H. T I cannot write because T stands for tail. Next, F, getting tail. Getting tail. Sorry, getting 7. Do we have 7? No, so empty. Next, G, getting head or tail. Do we have head? Yes. Do we have tail? Yes. So, G will be head, tail. Okay. So, this all if you see, let it be E. Yeah, E is having H, is containing S. F is empty. We know from chapter 6 that every empty set is a subset of the given set here. Same thing here also. Next, G is equal to, yes, that's what, no, the condition satisfied. So, E is subset of sample space. F is also a subset of sample space. G is actually equal to sample space. So, these all are events. Why? These all are subset, or we can say no, these are. So, now, having understood this, let us try to understand occurrence of an event. Occurrence of an event. When do we say an event has occurred? Very simple. Here's example. If you see here, H, right, is present in E. Nothing but this event has occurred. So, as soon any element is present in the event, then we say that event has occurred. Let us suppose that I have got one element B, that's outcome, dancing element outcome is not present in E, then event has not occurred. Okay. Now, for example, in this 7 has not occurred in this. Correct? That's why reason 7 is not present. Similarly, for this H has occurred. Correct? Now, having understood this, let us move on to types of events. Now, what are types of events? Same like no, in chapter 6 we have got types of sets. Here also. There we had what? Void set, null set or empty set. Similarly here, the names are a bit different. The first type is impossible events. Now, what is impossible event? An event E is said to be impossible if not even a single occurrence is present. For example, this will come under impossible event. Why? It has not occurred. because here we wanted 7, but in the sample space there is no 7. It's only a coin, correct? So example is here F. Next comes sure events. What is sure event? Any event E which is same as sample space, nothing but all the element of the event and the sample space both are what? Same. For example, G is equal to H comma T, which is same as what? Sample space. Therefore, G is sure events. Okay, sure event. Okay, event singular, only one, no? Next comes okay, elementary or simple event. Simple event, you should know the name, or elementary event. Whenever any event having only one sample point, nothing but only one occurrence, only one element, then we say simple event. So whenever the number of outcome of any experiment is, any event is 1. Okay. Now for example, E is equal to H is a what? Simple event. Okay. This I can say simple because number of occurrence are only 1. Actually, whenever we talk about any event, for example, let us suppose that we have got a sample space. I'm rolling a die. When I'm rolling a die, how many elements are there? 6 elements. Which are those? 1, 2, 3, 4, 5, 6. Now one question can be framed: how many simple event is possible? Nothing but number of events having only one element. I can have how many? 6. How, sir? Very simple, no? E1. Okay, just I'll take E, because you may think E1 when I write, you may think this one. Okay, E is equal to flower bracket 1, F is equal to flower bracket 2, then G equal to 3, H is equal to 4, I is equal to 5, and lastly J is equal to 6. That's it. So I can always say that coming to simple event, it completely depends on how many elements do we have in sample space. If I've got n number of element, nothing but events in the sample space, I'll be having n simple events, because I should write only one event in the what? Events. Okay, only one element in the events. So having understood this, let us move on to one more. Let us complete here only compound events. Now, what are compound events? See, whenever number of outcomes are more than one. So here, number of element, nothing but the outcome should be more than one, not equal to one, more than one. Now, for example, G is a compound event because it has got more than one element. So in this particular example, G is serving as sure event as well as what? Compound event. Why sure event is equal to sample space? Why compound event? More than one element. Okay. So in this case, it is acting as what? Compound event also. Now, having understood this compound event, okay. Now, having understood this, first make a note. We'll go for the next concept. Okay. Action. Dear students, having discussed the types of events, now the time is for algebra of events. So same like number system. After knowing numbers 1, 2, 3, then now the thing is what? How to add, subtract, multiply, and divide. Nothing but algebra of numbers. Similarly, we know the events. Let us suppose I've got two events. What are the different operations we can perform? So, operation on events. As I said previously also, the best way to learn this chapter will be comparing with chapter sets. Now, what are the different operations we had there? That is we call. First one was union, denoted by small letter u, where we have tried both common and uncommon element once. So A union B is set of all the elements such that X is either present in A or X is present in B. It's also understood that it can be present in both also. Let us be very clear with this. Okay. Next, second operation is intersection. So actually we are having a revision of chapter 6 here. Okay. That's why very easily you can get the marks now. 7 plus from this chapter. Intersection symbol. What's the definition? It is A intersection B. It is set of all the elements. Here we can say no, the elements are present X present in A as well as present in B. Here I have given the word and, nothing but common in both, present in both. Next comes the difference. When we say difference, yeah, A minus B, nothing but I want only those elements present in A but not in B. Okay, the occurrence. So set of all element X such that X belongs to A but X will not belong to B. The second set is B here. Similarly, B minus A is set of all element X such that X belongs to the first event. In B minus A, B is first, but X should not belong to B. Okay. Next is complement. See here, complement odd, complement event, odd. Complement means what? Deny. I don't want. So the other name, not. Okay, complement event or not, having a bracket. Okay, not A. For example, one event is a not A. So complement event of A. Okay, so it is given as A complement is equal to from sample space remove A. So what's the meaning? All the elements X such that X is present in sample space but X is not present in the event A. Okay. Now let us try to understand with the help of a diagram. See, when we are talking about the diagram, I hope it's recording now. Always doubt. See, here we have a sample space and this is my event A, following which our event B is here. So this region is common for both. This we call, this is what? A intersection B. This is an event present in only A. So it is A minus B. Nothing but what? Only A. Only A. Let's mention that A minus B is what? Only A. I want those elements present in only A. And similarly for this, what is the meaning? Only, I'll write it here. What's the meaning? Sorry. What's the meaning of this? Only B. So similarly here also, this is what? B minus here. From the diagram, very clear that if I take union of this part, see that we have shaded, okay? It is this one and this vertical and again here. So if I just take the union of all the three, nothing but A minus B, as a note we can take that if I take the union of A minus B, then A intersection B followed by B minus A. What is the union of this, this, both the circle? Both the circles what? A union B. Similarly, if I take intersection of A minus B, A intersection B and B minus A, do we have anything common? See carefully. It stops here. Here it is. Here it is. There's nothing common. Nothing but what will be the answer of this? It will be 5. Let us write it here. Second point, this is equal to what? 5. Okay. Having understood this, now let us take one problem from NCERT text. Okay, dear students, let us move on to the next problem. Let us move on to a problem. Question number 2 from exercise 4.1. A die is thrown. Describe the following events. Events are given here, and then we have to find this. I have taken all the operation so that whatever the operation we have discussed the concept, let us have a clear-cut idea. And this is also giving you a chance to revise chapter sets. Now, as you know, in this sample space is mandatory. A die is thrown. How many die? A single. A die is thrown. So, what will be the sample space solution? Sample space will be 1, 2, 3, 4, 5, 6. Any one of the outcome we are going to get when a die is rolled. I repeat, when a die is rolled, any one of the outcome we are going to have. Now, first we have to describe this event. Now, first event, number less than 7. So, coming to the first part, the first event A, number should be less than 7. If you see, all the numbers are less than 7. So, all will satisfy that they are less than 7. So, all are written. And let us try to recall types of events. This A is equal to S. Therefore, it is short events as well as compound events because we have more than one element. Okay. Regarding no? Yes. Next, B, number greater than 7. Do we have any number here greater than 7? We don't have. So it is empty. Under types of event, it is which event? Impossible events. One more thing, before I write here, you can see I am comparing with what? Sample space. Because sample space is what? All the possible outcome of the given random experiment. Now, if at all it is present here, only then I am going to write, otherwise no. Okay, don't forget event is subset of sample space. Next, C. Third problem C is multiple of 3. Do we have multiple of 3 here? Yeah, 3 and 6. So C is 3, 6. Next what? D. Number less than 4. Less than 4. Understand this. Less than 4. Already I discussed L. Okay, how you write L? Yeah, let us recall that. How to remember symbol? This is less than, and our L is also less. Both are matching, right? So less than 4. Which is the number? Which are the number less than 4? One is less than 4, 2 and 3. These 3 numbers are less than 4. 4 is equal to 4. 5 and 6 are more than 4. We want less than 4. So D. 1, 2, 3. E says an even number greater than 4. Define even number. Any number which is divisible by 2. I want only those number which is greater than 4. When I say greater than 4, 6, 8, 10 moves on. But I want with respect to this sample space. So my answer will be only 6. 6 is the only even number which is greater than 4. Understand this carefully. F is a number not less than 3. Understand this. Less than 3 means this. Correct? Huh? Not less than. I don't want that number. I want number not less than 3. Less than 3 means what? Which are the number less than 3? 1 and 2. I want what? I don't want less than 3. Don't want less than 3 means 3, 4, 5, 6. When you say 4, 5, 6. 4, 5, 6 are not less than 3. Yes. But 3 is also not less than 3. 3 is equal to 3. I repeat. 4, 5, 6. These are not less than 3. So surely all will write 4, 5, 6. But 3 is also not less than 3. Actually 3 is what? Equal to 3. So 3 should be also mentioned. I hope this point is clear. Many will forget to write what? 3. Okay. Now we are finished with the event. Now let us try to find one by one. I want A union B. Union means writing common, uncommon together. So here A union B. B I don't have anything. So only the elements of A will be mentioned. Job done. Next, I want A intersection B. Coming to A intersection B, it is what? Common element. Do we have anything common? Nothing. So empty. Next, B union C. Union means writing common and uncommon element together. B is here, C is here. There is no element here. So only 3, 6 is the answer. Next, E intersection F. E intersection F. Intersection means what? Common element. Come on, see E and F. What is common here? 6. That's it. Next is D intersection E. D intersection E. What is common between D and E? D is here, E is here. Do we have anything common? No. So empty set. Next, when I say empty set, I mean to say it is what? Impossible event. Nothing but the event has not occurred simultaneously between D and E. E intersection F means what? This is the event occurred. This is the event occurred. 6 is the event occurred simultaneously for both E and F. Okay. A minus C. I want only that event occurred in A but not in C. That's the meaning of that. Let's go step by step. A is 1, 2, 6. Minus what is C? 3 and 6. So the way we went for chapter 6, I just said think as a subtraction. So when I think as subtraction, 3 gone, 6 gone. What is remaining? What is remaining? 1, 2, 4, 5. That's it. That is your A minus C. Okay. After A minus C, I want D minus E. Coming to D minus E. D minus E. Again substitute. What is D? 1, 2, 3. What is E? 6. I want only that event which has occurred in D but not in E. As you can see, that there is nothing common. So again, it's what? 1, 2, 3 itself. When I'm saying nothing common, I mean to say there's nothing common to like this. No, 3 and 6 was there. So 3 and 6 was removed. There's nothing as such here to remove. See, before finding E intersection F complement, better find F complement first. Okay, let us try to solve this last two problem. First, we'll find F complement. As you can see, we have E intersection F complement. So, with this, F complement, as we know, it is from sample space remove F. Sample space is 1, 2, 6. Let us substitute here. Minus F. What is F? 3, 4, 5, 6. 3, 4, 5, 6. Now, very clearly you can see 3 gone, 4 is gone. Nothing but these are the common event occurring. We don't want common, only occurring in S. We want it's 1, 2. That is F complement. Now, let us find E intersection F complement. E intersection F complement is, what is event E? 6. What is F complement? 1, 2. What do we have common between them? Nothing. So, there is no occurrence between, common occurrence between E and F complement. That's the meaning of that. Kindly make a note of this. Okay, dear students, let us move on to the next topic, that is mutually exclusive events. Mutually exclusive events. Now, what is this mutually exclusive events? Here, I'll be defining with respect to 2 events, then 3, then in general. So, 2 events are said to be mutually exclusive if the occurrence is not common. Nothing but there is no common occurrence between them. Nothing but intersection should be always empty. What we call disjoint, there no. 2 sets are said to be disjoint. In the chapter sets, 2 sets are said to be disjoint if intersection is empty. Similarly, 2 events are said to be mutually exclusive events if there is no common occurrence. Nothing but intersection should be empty. Now, this, if I talk with respect to the diagram, I can have like this. This is my event A, this is my event B. This is with respect to two events. Okay. Now if I have got three events, coming to three events, let's suppose A is there, B is there, and C is there. When do we say it is mutually exclusive? Pairwise, it should be disjoint. Nothing but if I take A intersection B, it should be empty. If I take C, A to B over, then if I take B and C intersection, it should be empty. Again, if I take A and C, it should be what? Empty. So if I take Venn diagram, it should be like this. Pairwise, pair, nothing but at time two. There should not be anything common. Nothing but they should be what? Disjoint. Pairwise, when it is disjoint, on the whole also what? It is disjoint only. There is nothing common. Okay. Now, if I talk about in general, let us say A1 is there, A2 is there, A3 is there. Like this, we have AN. Then, with the help of diagram, you can go like this. Here E1 is there. Now we are coming out of circle. Now this can be E2. We are doing partition here. Then E3. This is E4. Okay, since I've taken A, no? And I take it A here. A. Okay. We can take whichever alphabet we want. Okay. There is no as such condition. A to Z we are free. Okay. Like this, I suppose here we have. Okay. A. We have A, N. So if I have got n number of events, pairwise, you can see pairwise A1, A2, there is nothing common. A1, A3, nothing common. A2 and A3, nothing common. A1 and AN, nothing common. Nothing but in general, AI intersection AJ should be empty. When I is not equal to J, only then we say it is mutually exclusive. So I went with respect to 2, 3 as well as n number of events. Now next one is, what do you mean by mutually exhaustive events? Okay, mutually exhaustive events. Ready? So again with respect to 2, just see this diagram. Now purposefully I am giving a boundary between them. I am not giving a circular because the definition for two events, no, if I take union should be equal to sample space. Now if I take this example, no, union will be this circle, this circle. There are so many things in between left out which will not cover the rectangle bracket. That's why we should know come out of from the usual things. Okay. So purposefully I have taken an integration symbol for upcoming year. Okay, it's coming anyway. What upcoming year? Hardly 2 months, no? 2 months. So A union B is equal to sample space. I mean to say within 2 months will be second year PUC students. Now, what if I have got 3? Again, if I have 3 events A, B, and C, for this to be mutually exhaustive, again union of all the 3 should be what? Sample space. Again, you see, if we take the diagram, sample space, again circle thing will not work. Let's suppose here this is A, this is B, and this partition is entire is C. So this entire is A, this is B, and this entire is what? C. So we can have common also, no problem. But if I take union, I should get sample space. So like this, in general, if I talk about the same, you can see if I take the union of this, I'll get what? Sample space. So I have also spoken with respect to general. Now see how we'll take A, I running from 1 to n. When I is equal to 1, I'll get, I'll write it. When I is equal to 1, I'll get A1. This symbol stand for union or union. Then when I equal to 2, put I equal to 2 here, A2. Again this symbol stand for union. Then I equal to 3, again union, moves on, union. Lastly, I is equal to n. So union of all this you can see from diagram, what you will get? The rectangle box, nothing but sample space. So with respect to all I have discussed, 2, 3 as well as n in number. Now when do we say combine? If I combine both, mutually exclusive and exhaustive. Mutually exclusive and exhaustive events. So here also with respect to 2, 3, any number we can discuss. See, both should happen. Nothing but if I take intersection, it should be empty. If I take union, it should be sample space. Now, for coming to 2, let's write here 2 events. Okay, it's understood here also, no? This is what? For 2 events, right? This is for 2 events. This is for how many events? 3 events. This was for 3 events. What about this? This was for n events. Similarly here also, this was for how many events? 2 events. Here 3 events. And lastly here n events. So now let us move on to 2 events. If you go for 2 events, so for mutually exclusive, intersection between the 2 events should be empty. And for exhaustive, if I take union, it should be what? Sample space. Similarly, if I go for 3 events, and so this diagram will be this, the ideal diagram. Okay. Next, for 3 events, pairwise, A intersection B should be empty, B intersection C, nothing but the event should not occur, then A intersection C should not occur. And if I take union of all this, and write and here properly, and if I take union of all the 3, I should get sample space. Similarly, if I take n in number, and for this diagram, let us give for this, no, for B, the diagram will be here. See carefully. Same I will take. Now just see carefully. This is A. This partition is B. This is C. If you take union of all the 3, you will get sample space, rectangle box. And A, B, there is no common. B, C, there is no common. A, C, there is no common. Okay. Lastly, for n events. For n events, what we can say? This is the ideal diagram. You take the union of all, you will get sample space. Take intersection pairwise, nothing is common. So I have to club this as well as this. So if I take for mutually exclusive, AI intersection AJ should be empty, where I is not equal to J. Yes, it should be for 2 different. If you take for the same, it will be what? Same event itself. What is A intersection A? A itself. And if I take union of all the events, I running from 1 to n, you should get sample space. Nothing but I am talking about this only. I written same thing in Chotu. Okay, same thing whatever I have written here. Okay, so with this, our first exercise comes to an end. Means concept. I'll take a problem on this. Then we'll take third exercise. Means second exercise. I said third exercise with respect to the old syllabus. Okay, make a note. Dear students, let us take problem on the concept just now discussed. Question number 1 from exercise 4.1. A die is rolled. Okay, a die is rolled. Since let's say a die, only one die, correct? Let E be the event, die shows 4. And F be the event, die shows even number. Are E and F mutually exclusive? Until and unless we are not aware about the definition, concept of mutually exclusive, we can't solve the problem. Now, since we know that for mutually exclusive, intersection between both the events should be what? Empty. Nothing but there should not be any common occurrence. So, because of this concept, we have to first find E, then find F, and then take the intersection. And if it is empty, it is mutually exclusive. Non-empty, not mutually exclusive. So, when a die is rolled once, when a die is rolled once, what is the sample space? S is equal to 1, 2, 3, 4, 5, 6. And E be the event, die shows 4. Die shows 4. Yeah, do we have 4? Yes. So E is 4. Then F be the event, die shows even number. Die shows even number. Which are the even number here? 2, 4, 6. Now, since I know the concept for mutually exclusive, I have to see the intersection. What is common between them? 4. Okay, there is a common occurrence between E and F. Therefore, this, as you know, this is not equal to empty. This implies E and F are not mutually exclusive what? Events. Kindly make a note of this. Okay, dear students, now let us move on to the next concept, that is defining probability. What are the axioms related to this? Okay, so we have got all the basic information about probability. Now let us move on. Okay, this is already done. Where is the duster? Yeah. Okay, now let us move on. Axiomatic approach. Axiomatic approach to probability. To probability. Listen carefully. There are some axioms. Recall in your school days also used to have axioms and postulates. What are those? It is some statement which is logically true without any proof we are going to accept. For example, length and length when added, the sum of the length will be larger than the given two length. It's common sense, correct? No? So like that, we are going to have some axioms here. So first let us try to understand the definition of probability. Now here, I would like you to understand with the function concept. Recall what is a function? A function is a special type of relation where every element have unique image. So f is a function from A to B. So on this we are going to define probability. So probability is defined as, let us suppose that we have a sample space S. Okay, first let us have a sample space. What is sample space? It is all the possible outcome of a given random experiment. What is random experiment? Recall, any experiment satisfying the condition that we should have two conditions satisfying. First, we should have more than one outcome. Second, in advance we should not be able to predict the outcome. So having this, now coming to probability P, it is a real valued function. Recall what is real valued function. F is said to be real valued function if my codomain is subset of real number or equal to real number. And for real function, A should be a subset of real number or subset of real number, equal or subset of real number. Now probability given by P is a real valued function whose domain is power set of S. What is power set? Collection of all the subset. So power set we denote by small, okay, denoted by P of S. This stands for power set. Power set of sample spaces, where its range is closed interval 0 to 1. So probability is a real valued function whose domain is power set of sample space and the range is closed interval 0, 1. Okay, satisfying some of the condition. What? First condition, if I take probability of any event EI, since it should occur, the probability value should be positive. It can also happen that it's not occurring, then the probability value should be 0. So get r equal to 0, where EI is subset of sample space. So what is the second condition? Second condition is if I take probability of any sample space, it's always equal to 1. Third condition, if I talk about two mutually exclusive event E and F, probability of E union F will be probability of E plus probability of F, provided E and F are mutually exclusive. We will understand this still better when I am going to give one formula of probability. Just first understand this. Now let us say that having this, if I talk about a sample space having the elements, the events occurrence means the occurrence as omega 1, omega 2, omega 3, up to omega n. Now from this, some of the things can be understood very clearly. What? Since probability of sample space is 1 and probability of event is greater than or equal to 1, we can always say that whichever probability we are going to find of the elements, it is always going to lie between 0 to 1. That's obvious for I equal to 1, 2, 3 up to n. Similarly, see carefully, because of probability of sample space is equal to 1, it also means that if I sum probability of omega and running from 1 to n, when I equal to 1 is omega 1, I equal to 2, probability of omega 2, I equal to 3, probability of omega 3, so on up to I equal to n, sum of this will be 1, because matter of probability ultimately becomes what? Sample space. One more point. What? If we are going to take probability of any event A, this will be summation of probability of omega I. So if at all, and where this omega I will belong to the event A. Okay, so these are the axioms with which we are going to work. Now let I take the definition of probability if the occurrence are equally likely to be there. Okay, the occurrence are equally likely, then the probability of any event A is favorable outcome divided by total outcome. Now whatever we have given here, the axioms, these two, we'll understand from there. First, we said it can be equal to 0 when if it is impossible event. If A is impossible event, let us also try to understand this point also and these 2 points also from this formula. See carefully. If, okay, first point, A is empty, nothing but impossible event. How many elements do we have in A now? Because there is no element present here, no event has occurred, means there is no occurrence here, so the value will be what? 0. Therefore, probability of A will be 0 by non-zero will be 0. That's what you can see. Probability can be 0, and here the least value of the probability is what? 0. It cannot be negative. That's what the range is closed interval 0 to 1. B point. Let us. So then, how come 1? Okay, very simple. See carefully. If at all A is sure event, nothing but A equal to sample space, then probability of sample space, wherever A is a put as there, number of favorable outcomes in sample space divided by again sample space, both will get cancelled. Probability of sample space is what? 1. That's what we have got here, and this is also saying that it can be positive, but it cannot go beyond 1. That's very clear. So the range of the probability is always between closed interval 0 to 1. Since it is a subset, don't forget this closed interval 0 to 1 is subset of R. We know every interval is subset of real number from chapter 6. So it is real valued function. I hope this is clear. And sum, if we take, it will be always equal to 1. So this is for equally likely outcome. Only then we are going to use this formula. Equally likely outcome. Okay. One last formula I would like to quote. Let I quote it here so that we are ready to start with the problem. See carefully. What's that? I think better you copy. We need some more space. Better copy it. Okay, dear students, let us move on to the next concept. See, now I want to go for some formulas which will be helping for us upcoming problems. Already I have discussed about probability of any event if it is equally likely outcome for any event A is favorable outcome divided by total outcome. Okay, where number of element in S should not be equal to 0. Only then, see, if there are no elements in sample space, there is no question about any experiment happening. Okay, so it should be not be equal to 0. Otherwise, mathematical definition, the denominator should not be equal to 0. Next, probability of union of two events. is same as probability of A plus probability of B minus probability of A intersection B. In this case, if A and B are mutually exclusive, nothing but intersection, nothing but there is no common occurrence, so intersection is empty, then probability of, just now we discussed, whenever it is empty, nothing but, now you can just go with this formula itself. See carefully, whatever A is there, same A here. Probability of any event is number of element by, in the event, divided by total number of element in the sample space. So whatever the event is the same event. Here the event is what? A intersection B. So n of A intersection B divided by number of element in the sample space, where number of element in sample space should not be equal to 0. Correct now? Now here how many elements do we have here? 0. 0 by non-zero is what? 0 only. So that's the reason, no, that probability of whenever it is empty, whenever it is, the event has not occurred, nothing but here, no, impossible event, that then the probability is always what? 0. If I substitute this in equation number 1, then see what we are getting. Equation number 1 will change to, from here, probability of A union B is equal to probability of A plus probability of B, and this will be 0. So P of B minus 0 will be P of B itself, nothing but probability of B. This will be holding good provided it is what? Mutually exclusive events. Only then you are going to use that. This will be general case. Next, see carefully, one diagram I'm taking here. If this is the sample space and this is the event E, what will be this region? Outside E but within the rectangle box. Is it not? That will be, I don't want E, nothing but E complement. So now we are getting one relationship between the E complement and E. See, from the diagram it's very clear that if I take the union of E and E complement, I get sample space, nothing but it is mutually exhaustive. And if I take the intersection between E and E complement, I get empty. That is to say that always we can remember that any event E and its complement are mutually what? Exclusive and exhaustive events. Exhaustive events. Now for this, I want to find what is probability of E union E complement here. Now if I try to find, now probability of sample space, we know it is 1 from the axiom, and we understood also how it is so. And now this, since it is mutually what? Exclusive. For mutually exclusive, you can see union is equal to sum of the two individual event. So since E and E complement is mutually exclusive, as you can see here, therefore what we can say? This will be probability of E plus probability of E complement. I want probability of E complement. So probability of E complement, if I transpose probability of E the other side, I get 1 minus probability of E. This will be a very important relation for us. It may happen that they may give you probability of value E. They want E complement. Always you can use this. And one more. Addition of probability of an event E and not E is always equal to 1. So this will be a very important result, both of this. Anyway, both are, we can easily, if I know this, it means I also know this. Both the ways it is true. Okay, so with this, all the concept we have done. Now only we are have to, means we are left with problems. So kindly make a note of this. Okay, dear students, now we are starting with model question papers. Here, the first model question paper of the academic year, as we are aware, it is 2024 to 2025 from PU board. Now, 1 marker. See, we are getting one question in 1 marker, one question in 2 marker, and one question in 5 marker. So 1 plus 2 plus 5 will be 8. That's what I have mentioned, 7 plus marks. Okay. Question says the number of simple events corresponding to the sample space. 2 coins are tossed once is. They want what? Simple events. Recall, what is simple events? Nothing but elementary events. Any event having only one element. So how many simple event can we have? Nothing but how many event can we have having only one element? It's very simple. First, see the sample space. Sample space, I said 2 coins are tossed once. So sample space equal to, it can happen that both the time when I'm both 2 coins are there. Okay, yeah, 2 coins are there when I'm tossing. Both can give me head. It can happen that first coin is giving head, second is giving tail, or it can happen that first coin is giving tail, second coin is head, and both are tail. As soon as you write the sample space, see, whatever number of elements are there, those many elementary events or simple events we can have. How? I can have one event E1 with HH. One more event I can have E2 with what? HT. Many students will count this as 2. No. We are talking about number of outcomes. When 2 coins are tossed, this is only one outcome. It means first coin gave head, second coin also gave head. Here, first coin gave head, second coin gave tail. Then first coin gave tail, second coin gave head. Lastly, both gave tail. So how many possible? 4. Option D is correct. But in place of writing all this, I am saying number of simple event is same as number of element in sample space. How many are there? 4 over 4. Okay. Now, coming to 2 marker question. A fair. Okay, before that, option D. I usually write like this because I have seen student after we say no, option D is correct, they will have a trouble to tick. So I tick here also and I write here also. Okay. A fair coin with 1 marked on one face and 6 on the other. Be careful. Usually for a coin problem we have head tail. They are saying it's not like that. One face is marked with 1, other face is marked with 6. And a fair die. Fair, what my fair? Unbiased, no partiality, equal chance of outcome. So a fair die are both tossed. Coming to fair die, they are not mentioned anything. It means what? Fair die will have numbering from 1 to 6. Find the probability that the sum of numbers that turns up is 12. First, let us write the sample space. To write the sample space, just take a table here. Don't fill anything, just try to have the idea. Here we'll take coin. Okay, here we'll take coin. And here we'll take die. Coming to coin, they said it is marked with number 1 and 6. So I'll write it here 1 and 6. Okay. And let us have one more here. Far away. Little one more I want line. Here it's a die. And coming to die, we know the outcomes are 1, 2, 3, 4, 5, 6. Only for visualization I have taken this. Don't fill anything here, fill in the sample space. So that you are getting clarity also and nothing is missed also. So now when I am going to get the entry here, the entry is what? 1, 1. What is the meaning of this 1, 1? This one is saying coin gave me 1 and die gave me 1 here. Similarly here 1, 2. Correct? No. Here I had 1 here and 2. 1, 2. What's the meaning of this? When I was rolling die and tossing the coin gave 1 and die gave 2. Why coin gave 1? Don't forget, in our problem they have said one face is marked with 1, other face is marked with 6 on the coin. Okay. So next, now 1, 3. I hope now from here it's clear. Then for this 1, 4. Next 1, 5. Here 1, 6. Now here 6 and 1, 6 comma 1, next 6 comma 2 for this, then for this 6 comma 3, next one is 6 comma 4, 6 comma 5, lastly 6 comma 6. And how to be assured that yes, this many, very simple. Before this I uploaded permutations and combinations. There we discussed fundamental principle of counting, correct? Now, so see carefully here that here when I'm talking about coin, I have got how many outcome from the coin? 2. And for the die, how many outcome? 6. So since one after the other it is occurring, I can multiply them. 2 6 are 12 and count how many are there? 1 2 3 4 5 6 7 8 9 10 11 12. Okay. Next, let us go to the question what they want. I want the probability that the sum of the numbers tends to be 12. So E, whatever they ask now, that you take as an event. Sum of the numbers should be 12. Sum is 12. No need so much. Okay, this is enough. Now I have to find those event here from the sample space that if I sum them, I should get 12. And just see, this is the only one. 6 plus 6 is 12. Whereas here 6 plus 5 is what? 11. And all these are less than 12 if you take the sum. Why we are taking sum? They said very clearly, find the probability that sum of numbers that turns up is 12. Whatever the die and the coin we are rolling, die we are rolling and coin we are tossing, whatever the output we get, if I sum means what? Addition. If I add them, I should get what? 12. This is the only one outcome. 6 plus 6, 12. See this? 6 plus 5, 11. I'm not getting. 6 plus 4, 10. This will give 9, 7. You can see all are decreasing. So this is the ultimate. Now what is probability of any event E? It is favorable outcome divided by total outcome, where total outcome is not equal to 0. Favorable outcome we have only 1. Again, don't count as 2. It is not about number of element, it is number of outcomes. Okay, so it is how many? 1. Total outcome how many are there? Count. All we saw, no? 12 it is. So 1 by 12 is the answer. Okay, I hope the things are clear. Make a note. Okay, dear students, let us move on to the next problem, which is a 5-marker question from the same model paper. Question says 3 coins are tossed once. Find the probability of getting. First subproblem 3 tails, second subproblem exactly 2 tails, third subproblem no tail, and fourth subproblem at most 2 tails. Coming to the solution, as usual, first I want sample space, and here 3 coins are tossed once. So now how to write the sample space? Very simple. Since we have 3 coins, first coin gave head, second coin gave head, third coin gave head. Now it can't have more than 3 heads because only 3 coins. Now we have achieved heads, 3 heads. Now reduce number of heads. Now let us suppose that I am reducing by 1. So it is tail here. This says first coin gave head, second coin gave head, third coin gave tail. Okay. Now shuffle T. Now if I write T in the middle, I'll get H, T, H. Lastly, T, H, H. So there, here I have mentioned all the different possibilities of writing having 2 head and 1 tail. There are no more, right? Now what we will do? Decrease till number of head. Here we had 2 head. Now we will write head, tail, tail. Nothing but I want only 1 head. And other 2 coins are giving tail. Now again shuffle this. Nothing but head you can write at the middle and at the last. Nothing but rightmost. So this will be tail, head, tail, 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 head. This is all the possibilities having 1 head and 2 tail. So here we have 3 head. Here we had 2 head. Here we have 1. Now all should be what? Tails. How many outcomes are there? 1, 2, 3, 4, 5, 6, 7, 8. Even if you want, you can have one formula for coin. Number of elements sample space. For the coin, how many outcomes? 2 outcomes to the power number of outcomes. I repeat. number of outcomes in the base, power will be number of time experiment performed. Okay, last time I just said wrong. Number of times the experiment is performed. How many performed? 3 times. So answer is what? 2 power 3, nothing but 8. Okay. Now let's go one by one. First problem. They said 3 tails. See, whatever they're asking, that is your event here. Okay, we can change to B, C, D also. Now here, 3 tails. Do we have that? Yeah, here. So A is equal to T, T, T. What is probability of any event A? It is favorable outcome divided by total outcome. What is the favorable outcome? 1. And total outcome is 8. So 1 by 8. First part done. Okay, let I write this properly. I have a doubt what you may think as. Is it something like y8? Second problem, exactly 2 tails. I'll take B as an event. Exactly. Whatever they're asking, that's our event. Exactly 2 tails. Now see which are those events having only 2 tails. Means here. So coming to 2 tails. Yeah. 2 tails. Can you see? 2 tail here, 2 tail here, 2 tail here. Exactly 2 tails. So these 3 I have to write. So let us write down. B is equal to HTT, then THT, TTH. So probability of B is favorable outcome divided by sample space, nothing but total outcome. See, whatever you have got here, since A, so it is A. Now this B, so it should be what? B. Simple as that. Favorable, how many? 3. Total, how many? 8. Already we got here, no? Total is always 8. Next. No tail. I want that outcome in which there is no tail. See, no tail. Which is that reading in this where we don't have a single tail also? It is this. Remaining all you can see T. Okay, don't forget here in all our discussion, H stand for head, T stand for tail. So H, H, H. So probability of C is favorable outcome divided by total outcome. How many outcome you have got? Only 1, not 3. You're not counting how many outcome is there. When 3 coins are tossed, I got head, 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 1 outcome. Okay, divided by total. Then see the last one, utmost. Fourth sub problem. Let us suppose E we will take what? Utmost what? 2 tails. Utmost 2 tails. Utmost means which symbol? Let I write it on the top. Remember this. Even in permutation and combination we discussed, whenever it is the word at least, it is always greater or equal to. For the word at most, it's always less or equal to. Let you have beside the chapter name so that you always remember. So at most is less or equal to. How many? That will be given in the question. 2 tails. So it means maximum I want 2 tails, minimum no tail. Minimum no tail. Many students know when we ask minimum, they'll say 1 tail. Because in their head now, thought is tail should be there because tail is mentioned here. And then listen here, less or equal to. It means what? I can have 0 number of tail. And 0 is less than 2. 0 is less than 2. So max to max 2 tail and minimum is 0 tail. Nothing but except this. Here we have 3 tail. Removing this, here we have 0 tail. Here we have 1 tail, 1 tail, 1 tail. Here we have 2 tail, 2 tail, 2 tail. So we should write all this. Correct? All this. Totally 7. We are going to have the occurrence. 7 occurrence will be there. So let's mention again. H, 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 T, H, T, H, T, H, 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 T, 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 H, T, 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 H. Let us just see have I done everything correctly. And one more thing is when you are writing, order is not important. HTT, THT, TTH. I mean to say when writing letters of person, you wrote this one first, no problem. I just went in one particular order, like first 3 heads, then reduce the head by 1, so we have 2 heads, then shuffle T, then here we have only 1 head and there is no head, so that we have not missed even a single occurrence. Now probability of the event E is favorable elements, no, it's the number of favorable outcome, I mean to say, divided by total outcome. How many are there? 1, 2, 3, 4, 5, 6, 7. Divided by total occurrence, how many? 8. That's it. Okay, kindly make a note of this. Yes, let us move on to model question paper number 2. Again, same pattern, part A, 1 marker question. This is same as the 2 marker question of the model paper 1. Question says the probability of getting exactly 2 heads on tossing a coin thrice. You want 2 head. Actually, I forgot that this is same as the previous. I could have not erased anyway. Sample space already explained how to write, so let us write faster. Already I discussed in the model paper number 1 for 2 marker. So same thing, what I did there. Then HTT, shuffle H to the right, and all T and all tail. Now they said exactly 2 heads. So event A is what? Exactly 2 heads. Exactly 2 heads. You can see this. So exactly 2 heads. So A if H T H T H T H H. Probability of favorable outcome. Probability of A is favorable outcome divided by total outcome. Favorable how many? 3. Total how many are there? 8. 3 by 8. Option C. Now comes from part B, 2 marker question. If probability of A is 2 by 3 and probability of B is half, find probability of A or B and probability of A and B if A and B are mutually exclusive. If we don't know the concept of mutually exclusive, gone case. And one more thing, remember, whenever you see the word and, it is intersection. Whenever you see the word or, it is union. Right beside the chapter name itself. Better. So coming to the solution of this, they said it's mutually exclusive, therefore A intersection B is empty, following which probability of A intersection B should be what? 0. Already we have discussed the concept before starting the problems. Now, first point, I want probability of A or B. What's the meaning of or? Union. So I give one formula also for exclusive events. It is P of A plus P of B. What is P of A? Probability of A value 2 by 3. What about probability of B value? Half. LCM of 2 and 3 is 6. 6 by 3, 2. Multiply 2 here. 2 2s are 4. 6 by 2 is 3. Multiply 3 here. 1 3s are 3. So 2 3s are 6. We are getting how much? 7 by 6. That is more than 1. For a while, let us check. Okay. 6 is the LCM, right? 6 by 3 should be 2. 2 2s are 4. 6 by 2 is 3. 1 3s are 3. If this is the question, then this is the wrong question because probability will vary between 0 to 1. Let us check the question. If this question entries are taken correctly by me, then it's a wrong question. Grace should be given for this. Question number 29. 2 by 3 and half. Okay, I have copied the data correct. Even if we convert to decimal, you see carefully, this is 0.5, correct? No, 1 by 3 is 0.3. 3 moves on. Into 2 will be 0.6. The addition is how much? 1.1. So this is not coming to. So this will be a wrong question. See how we can know whether the question is wrong or not, because of the concept. Since we know from the concept probability of any event is between close interval 0 to 1, we got it. Okay. Anyway, coming to this part. Anyway, the value should be changed, but let you understand how to solve probability of A and B. It is in the question only. And means what? Intersection. What is probability of A intersection B? 0, because they said it's mutually exclusive. This will be 0 irrespective of these two values, because it is mutually exclusive. So it's a wrong question. Okay. Kindly make a note of this. Dear students, now let us move on to the next problem, a 5-marker question from second model paper. The question is on pack of cards. Okay, so let us have a flow chart here. In examination, flow chart will not be given to you. You should learn that. So let us have a flow chart. See, coming to pack of card, 52 pack of card we have got. Okay, 52 cards we have got in normal pack of cards. Now 52 by 2 will be 26. So 26 cards will be black in color. How many cards? 26. The other 26 card will be red in color. So I'm writing in blue, because last time I saw that when I'm writing in red, the things are not so visible the way it is there in blue ink. So it is red here. Again, 26 divided by 2. Why I'm saying repeated divide by 2? So you understand how to remember the count. 52, if you remember, 52 by 2, 26. Again, 26 by 2. I have got 2 more division. Here, it is spades. 26 by 2 will be 13. And here, clubs. Again it is 13. Whereas coming to red, again if I divide 26 by 2, I get hearts. How many number? 13. And diamonds. How many number? 13. Now the question is, which are those 13 cards? Those cards are 2, 3, 4, 5, 6, 7, 8, 9, 10. First you see, 2 to 10 is 9 cards. One is missing here, okay? 2 to 10 is 9 cards. Then A, K, Q, J. So from here to 9, then 10, 11, 12, 13. So this 13 cards, numbering from 2 to 10, then what is A? A stands for ace. K stands for king. Q stands for queen. J stands for jack, not joker. Joker, if it is there, it will be more than 52. In normal pack of cards, joker is not there. So spades will have all these 13 cards, club will have all these 13 cards, hearts also, as well as diamond also. So since we have 4 division, and each of this cards spent here, 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 how much is 13 into 4? 4 3s are 12, borrow 1, 4 1 are 52. Yes, it is. So each card is there 4 times. Okay. For example, card with number 6, how many times is present? 4 times. How? It is there in spades also, clubs also, hearts also, diamonds also. Similarly, card that is queen card. How many? Again, how many? 4. It is there in all. 1, 2, 3, 4. Now, if I ask, how many card do we have in spade with number 3? Spade with number 3, only 1 card, because I want only a particular thing I'm asking. Okay. Now, having this question, having this concept, let us go to the question. Question says one card is drawn from a well shuffled of 52 cards. If each outcome is equally likely, calculate the probability that the card will be. We have 4 sub-problems. Let us take one by one. I think we should be able to complete in one stroke. Okay. First one is a diamond. So whatever they are asking, we are going to take as a one which you have to find a diamond. And they want to withdraw only one card. Before that, don't forget probability of any event is favorable outcome divided by total outcome. So coming to total number of outcomes are how many? 52. Now favorable outcome. What one? Diamond card. Total number of diamond cards, how many? 13. Divided by total is 52. This is one way of understanding. But actual way of understanding is from combination. Understand how many cards are drawn? 1. Correct? No? 1. Now, I want to withdraw diamond card. Come here. How many diamond cards do we have? 13. Out of 13 diamond cards, I want to withdraw 1. Nothing but out of 13 diamond cards, I want to select 1 diamond card. Nothing but this is actually 13C1 divided by out of 52 cards, 1 card is drawn. So out of 52, 1 is selected. Now the question mark is why we are not using this logic. See, whenever it is 1 card, no, we know from combinations, NC1 is what? N. Whenever you are taking only 1 element to be selected, whatever number is the same number we are getting, no? So even if we avoid combination also, we are getting the same answer. But as soon as it is more than 1 card, then without combination, you cannot solve the problem. Okay, so 13C1 because of this logic is 13. 52C1 will be 52 itself. So both are same. But I wanted you to understand what is happening here. Okay, fine. So 13 ones are 13, 13 fours are. So answer for the first part of the problem is 1 by 4. Next, not an ace. See, here we can solve this point 2 ways. Coming to B part, they said not an ace. Let us draw one line here. I don't want ace. So either I can think of calculating other than ace card. That is a time consuming. We know one result. See, I can write like this, probability of B. I don't want ace is same as, see this carefully, what is probability of E complement? 1 minus probability of E. Means I don't want E. 1 minus I want E. Nothing but from 1. Remove that. The one which I don't want. So here also, not an ace card, no. So see carefully. 1 minus probability of B complement. B is not an ace card. So what will be B complement? Ace card. An ace card. Okay. Let us write an ace card. I hope an ace card. I hope this logic is clear. So I am only concentrating on ace. Okay. 1 minus. Again the same definition. Favorable by total. How many? Let us write this also. Since we had A, it is A here. Since we have complement, it will be what? Number of element B complement divided by means occurrence. Occurrence I mean to say. 1 minus B complement is I want ace card. And out of how many ace card do we have? Each card is at 4 times. So out of 4 I want to select 1. So 4C1. 4C1 is what? 4 divided by total number of cards. Or out of 52, 1 card is drawn. So now from here, 4 ones are, then 4 13s are. So what's the value? 1 minus 1 by 13. Here it is 1. LCM, I can take 1 and 13 to be 13. 13 by 1 is 13. 13 into 1 is 13 here. Minus 13 by 13 is 1. 1 into 1 is 1. So our answer will be 12 by 13. This will be the answer for P of B. If you want the other way without taking complement also can be done. How, sir? What they said? Non-ace card. Totally Let us give the alternate or the alternate solution. No, sir, I don't want to use complement. I purposefully brought this complement so that you understand how to use complement concept. So the alternate probability of B is number of occurrence in B divided by total number of occurrence. B is what? Not an S card. Totally, how many S card do we have here in the question? I don't want S card, no. Out of total number of cards are 52. Out of 52, 4 cards I am removing because I don't want ace card. How much is 52 minus 4? Minus 4, it is 48. So the answer will be here 48 divided by 52. Simplify now. 4 table, 4 ones are, 4 twos are. Then here 4 ones are, 4 threes are. Nothing but 12 by 13. Same answer. Okay. So why we subtracted 4? Because 4 cards are ace. 4 cards are ace. And now this is what? Non-ace. Nothing but card not containing ace. Whichever you want, you can go ahead. Okay. Make a note of this. We'll continue the remaining 2 problems. First, make a note of this. Okay. Dear students, let us move on to the third sub problem. Don't forget number of element, nothing but total outcomes are 52. Now, third sub problem. Black card. See, there is no need to specify this. Coming to black, we had spades and clubs. Okay. So now, let us say C, I want black cards. Again, the same. Probability of C. Purposefully, I am using different letters. Let us not fix to A always. Favorable outcome divided by total outcome. Now coming to black cards. Out of 26, any one is taken. Actually, this is the logic. 20 out of 26, any one card. Since NC1 is N, this will be what? 26. That's what directly writing. Divided by 52 again. Same old logic. Now here, 26 ones are, 26 twos are. So answer is half. Answer is half. Now let us move on to fourth. Not a black card. This time it is very simple. Already we have solved the problem for what? Black card. Now this time it is what? Not a black card. Sorry, try to take complement of this. C complement. When C is black card, C complement is what? Not a black card. So what is probability of C complement? It will be 1 minus probability of C because of this formula. Probability of E complement is 1 minus probability of E. So what will be this? Probability of C is half. So what is 1 minus half? Half itself. So with this, we have completed all the problems of model question paper 2. Kindly make a note of it. Okay. Dear students, now let us move on to model question paper number 3. And again, a 1 marker question from part A. If A is any event associated with a sample space yes, then they are asking among this option which is correct. Now this is purely concept. We discussed definition of probability, that it's a real valued function where the domain is power set of the sample space and the range is lying between closed interval 0 to 1. So here you see, let's again go P. Probability is power set of sample space and the range is closed interval 0 to 1. Correct? So it also means what? Since power set, no. So probability of any event is going to surely lie between 0 to 1. Okay? Where A is any subset of sample space. That is an option A. Okay? Now let us move on to the next problem. Recording, no? Consider the experiment of rolling a die or I repeat, consider the experiment of rolling a die, single die it is, okay. Let A be the event getting a prime number, B be the event getting an odd number. Write the sets representing the events A or B, and B part is A but not B. They're not asking you to solve the problem. They want you to write a set form, nothing but the Venn diagram, and you have to represent these two. First, let us try to write down the sample space. Since a die is rolled, what are the possible outcomes? Either 1, 2, 3, 4, 5, 6. A be the event getting prime number. Define prime number. Any number greater than 1 divisible by 1 and itself. So 1 is not a prime number, 0 is also not a prime number, okay? They are neither prime nor composite, 0 and 1. So greater than 1 divisible 1 and itself. So 2, 3, 5 are the prime numbers. Next, B be the event getting an odd number. What are odd numbers? A number which is not divisible by 2. Which are those numbers? 1, 3, 5. 1, 3, 5. Now, coming to subproblem A. Write A or B. First, no, let us have this, no, A or B. Or means I said you union, writing common, uncommon together. So 2. Okay, let us write in ascending order. 1, 2, 3, 5. 1, 2, 3, 5. Right? Anything is missing? 1, 2, 3, 5. Now, if I take the Venn diagram, here sample space, and here we know that it is event A, and here we have event B. When we are going to write, common element should be mentioned here. What is the common element between the both? 3, 5, right? Let's make this one bit bigger, bit more bigger, the common region. Okay. So 3 and 5 here. Okay, comma. Then this side is what? Only A. Only A is what? Now see 3, 5. From here 3, 5, then 2. Yeah, this is 2. And coming to be 1, 3, 5. So 3 and 5 is that 1 here. Actually, in this itself, no, not only A union B, this entire is A union B. Now coming to A minus B, from this diagram this is very clear. Okay, I want what? Only A minus B. A minus B is only 2. That's it. This is the region what? A minus B. And this entire region is what? A union B. A very good concept level question. This entire thing shading is what? A union B. The entire thing shading is A union B. Okay, but let us suppose you want A minus B. Then also we can find here 2, 3, 5 minus B. B is 1, 3, 5. Remove the common. 3 gone, 5 gone, remaining is only 2. That's what you got here. Only 2. Okay, kindly make a note of this. Dear students, we are with the last problem from this chapter on this model paper. But after this, I want to discuss one concept, means a problem which is going to highlight a very good concept. Okay. But before that, let us complete this 5-marker question. This is there in NCERT as an example problem. So first I will be solving the way it is given in the NCERT text. Then I am going to give one alternate method by using permutations and combinations. That's the reason after permutation and combinations, first after permutation and combination, I am going for this chapter. Okay. Now let us proceed with the solution. See here, coming to number of element in sample space. Surely by using permutations and combinations, we can understand before writing the sample space how many elements will be there in sample space. See, how many cities are there? 4, nothing but 4 objects. So 4 boxes. Correct? Yeah. Now I have place A, place B, place C, place D to visit. Veena has to visit. It can happen that here, no, any one of the 4. Now, as soon you have went for one place, again you're not going to go for the same place. So let us suppose that B gone. Remaining how many? 1, 2, 3. Yeah, any of the 3. This is gone. Then 2. Anyone gone. Then C is only place. 4 into 3 into 2 into 1 is 24. This will be the number of element in sample space, which I have got before listing out the element. Let us see whether it is true or not. Let us list them. So coming to the sample space. So first let us fix A. When I fix A, let us write it here for convenience. Okay. Now when I fix A, now when I fix B also, nothing but the first place she visited was A followed by B. Okay, now CD. This is the order. Now as soon as I fix AB, I can extend this to, so I'll get DC. As soon this is done, with respect to A, means with respect to B, fix all possibilities done. Now A keeping as it is, in place of B in the second position, now we'll take C. Then what will happen? BD, correct? Since C is fixed, B and D. Next, AC as it is, now extend this to. What is the meaning of this? She visited first A, then C, then D, then B. Whereas here, visited A, then C, then B, and lastly D. With respect to C also done. Now I will fix D. So here after D, BC, as we can see here, this two are fixed for BC, or the other choice will be CB. With respect to A, visiting first all done. So here I have made sure A is visited first. Now it is B. As soon as I say B, now B is fixed. A, C, D. So A, C, D. Then B as it is. Again A, extend them, D, C. Then after that B. Now A part done. Now take C. As soon as I have taken B and C, AD. Then again BC, D, A. Next C part done. Here A part done. Now it is D, P, D. Now BD is done. So AC, then BD, CA. Okay. After this has been done, now B, visiting B first is done. Now take C. Nothing but we are assuming, means we are taking all the possibility that after she visit C as the first city, then what about the remaining? So again, as soon as C is gone, A, B, D. Then again CA fixed, extend this, DB. After again CA part done. Now CB. Here orders are important, correct? No? CB done. Then should be AD. Again CB as it is. AD will become DA. Next B part done. Now we'll take CD. So AB. I hope now the things are very clear. Lastly, now D is the first place to visit. So now A, since D is fixed, ABC. Then after D, A, these two we can exchange. Then after A is fixed in the second place, now it's a turn of other alphabet, means other city B. So after B, A, C, again D, B, C, A. Then with respect to again D, see B is over, A is over. Who is left? Now D. Means C, I mean to say, D is all there, C. Then AB, then again D, C, B, A. All the possibilities are done. So this is your sample space. Now count how many are there. And let I be very clear here. The first row is talking about A. first city to visit. Here it is here. In the second, we have fixed B to be the first city. Third, it is third row is C be the first city, and this is the D. The last row stand for the first city. Veena is visiting D. Now you can see in each 1, 2, 3, 4, 5, 6, and we have in each of the rows 6. 6 into 4, 24. That's what we got directly. This is the advantage of permutations and combinations, that without listing also we can say the answer. When I complete the problem, then I will solve this problem by using permutations and combinations logic also. First, let us complete. Now, what they want? A, B is used now, D, E all this. So let's suppose event E is what? A before what? B. I want that event in which she should first visit A before B. Nothing but before visiting B, she should visit A. Nothing but A should come before B. A should come before B. See which are those possibilities. A should come before B. Yeah, A is coming before B. This. A is coming before B. Again A before B. A before B. A before B. A before B. Here is A after B. No, no. Here all in this case B is coming first. No. A before B. A is before B. Here A is after B. After B. A is before B. After it is. A is before B. A is again before B. After A is again before B. That's it. So let us write all this. I hope this is clear. A, B, C, D here. Then A, B, D, C. A, C, B, D. A, C, D, B. A, recording no. Yes. D, no. Many times I'll have, because I am the editor. I am the director. Everything I am only. So here no one. Here C, A, B, D. C, A, D, B. C, D, B, C, D, A, B, I mean to say. C, D, this one. C, D, A, B. Then what next? Here D, A, B, C. Then D, A, C, B. Then D, C, A, B. D, C, A, B. Have you missed any? Let's check this. Okay. Okay, fine. Now let us write down what is the probability of the event E. It is again favorable outcome divided by total outcome. Ink is less for a while. Yeah, now better, because it is getting lighter. I am not happy with that. Now how many elements are there here? Come on, count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Totally we have 12 divided by total number of elements, that's where the events I mean to say is are 24. Now from here simplification, can't we say 12 ones are 12 twos are, so probability of E is half. Let's complete the next part. Second sub problem. What? A before B. Okay, again A should be before B, but B should be before C. So it should be like this. It means what? A, then B, then C. A should be before B and B should be before C. So I should have this alignment. In between, some other alphabet can come, but this should be the order. Now just see A, B, C. This one, let us stick in like like this cross we will give. Okay, this is there. First A, B, C. A, B, yeah, A, B, C. This also okay. Cross means we have to take here. No, after A, she is going to C, but what they said, A before B, then B should be before C. So here, before going to B, she went to C. Out means I should not take. So it should be ABC. Just see ABC, ABC. ABC. This one I can take. Again A, C, B. No. Here the order set all complete. The thing is changed because B is first always. First should be what? A first. Then again here C is always first. Gone. Here you see ABC. This is taken. ABC. A, C, B. No. B, B, B. No. So now let us suppose F is that event that A before what? B and B before C. Let us write it here. Nothing wrong. Now see carefully. Let us write down this. The cross one. A, B, C, D. Followed by A, B, D, C. Next. A, D, B, C. Followed by one more cross. Any more cross? No here. Here. No. Here. D, A, B, C. Any other? That's it, no? Yes. Now let us write down the probability of F. It is favorable outcome divided by total outcome. How many? 1, 2, 3, 4. Divided by 24. So 4 ones are 4 6 are 24. Answer is 1 by 6. Now let us, okay, therefore conclusion. Therefore probability of F is 1 by 6. 5 marks then. Now can we have any alternate for this? Writing sample space, then writing this. Yes, we have. Just dear students, having completed this problem, okay, here this is E is missing. Okay, before C. So now let us move on to the alternate method. This problem is done. 5 marker is done. As I said, let us try to go alternate method without writing all this. Can we get the answer? So at the beginning, I just made you understand that how we can get 24 as the total number of outcomes even before writing the sample space. Now recall the alternate method I am going for. Alternate. So anyway, number of element in sample space is 24 that we already discussed. Now coming to the first part, what they said, A means Veena should visit the city A before what? B. Totally how many cities she has to visit? A, B, C, D. So totally 4. So it means I should have 4 boxes. Now when I am talking about 4 boxes, see carefully. It can happen that Veena out of A, B, C, D, first she has visited A. Now here, as we know from permutation and combination, whatever inside, those are number of objects. Now here I can say number of city visit. So now here, since here, let us suppose that case 1 here, about the first place to visit is A. So 1 place. Okay, because A. Now the remaining are B, C, D. So either here or here or here, B or C or D. 3 places she can visit. So this box can take any one of the 3 cities. Nothing but can be either B. After visiting A, she could have went for B or C or D. So any one of the 3 cities. Let us suppose that C is gone. So now here how many? 2. 2 B or D. So 2. Let us suppose that D is gone. Then B is only 1. So totally 1 by fundamental principle of counting, multiply them. 1 into 3 into 2 into 1. Answer is what? 6. So if you see here also, A when we have fixed, see A first place. So 1, again A first place, 2, 3, 4, 5, 6. That's what we got. Without writing, we got. That's a part of permutations and combinations. It can happen case 2. What is case 2? It can happen that A can be here, nothing but she visited A as a second place. But don't forget A should be before B. So here, before we go ahead, let us try to fill which are the other places can be filled here. Now for this place, since A should be before B, here either C or D should be filled. Nothing but either she should visit C or D, any one of the two places. In which let us suppose D we have taken. So now here, okay, here already one because A. Okay, now here you see D is already taken here. So either C or B, any one of the place. So 2 and then 1 here. So multiply again by fundamental principle of counting. 2 into 2 into 1 into 2 into 1. 2 2s are 4. Just see if A is in the second place. 4 possibilities. Just see A is in the second place. So 1, then 2. A is in the second place. Say 1, 2, again A second place. 3, A second place. 4. Yeah, we got 4. Without writing. Next, let us complete here. Next scenario. What? Here, Veena has visited first A city. Here it is in the second place. Now it will be in the third place. As soon as I say third place, see carefully. A here, so nothing but 1. So now surely here this 2 place it should be either C or D. Why? If I write B here, but it will go against the question that A should be before B. So CD, any one of the two letter either here. Okay, as soon as I wrote here 2, any one of the letter means city should be fixed. Let us suppose D is fixed, so remaining is C, only 1. Now surely this is 1 for what? B. So total number of ways what? 2 into 1 into 1 into 1. Answer is what? 2. Now just see A is in the third position. Come on, see A is in the third position. Yeah, here 1. Okay, A is in the third position. Yeah, 1. Only 2. That's what we got. Now we have multiplied by using fundamental principle of counting. And now listen, we are going to total this. Sir, why we are totaling? Why we are multiplying? Or why we are using addition rule? Why not multiplication rule of fundamental principle of counting? Simple. I said there in permutations and combination, multiplication acts as and. After one, the other even should occur. Whereas addition rule work as or. Now you see, when we have said Veena will go to the first place A, simultaneously she cannot be in A second place. Correct? No, anyone it should be. Similarly, this also A is see here A is in the first place, second visit place, third visit place. Simultaneously she can't, or one after other she can't. Correct? No. So now by what? Addition rule. Addition rule. Okay, of fundamental principle of counting. I could have filled fundamental. This is better. Principle of counting. Principle of counting. What's the answer? Come on. 6 plus 4 plus 2. What's the answer? 12. That's what we got. 12 divided by 24. This part remains the same. Without writing anything, we got it. First, make a note. I'll erase this and then we will go for the second part. Okay? Make a note of this. Let me take the eraser. Means the cloth. Now, let us move on to the next part. See carefully. So, any first part done, so I can erase. I have also taken down and so if at all you are going for this way, then after you complete this, you have to copy down this entire part, right? Now see carefully the second. In second, they said B means A before B and B before C. So alternate for second problem. A before what? B and B before C. Again, how many boxes? 4. Why? 4 places. Now listen carefully here. A should be before. Again, I'll fix the first place. Let us suppose the case 1. What is case 1? Let us suppose A is there here. As well, I'm going to fix A here. Only one place. Now, coming to this. There is some condition here. Now, when I fix B, let us suppose here. C coming here too, no problem. But if I fix B here, I should make sure that C should be only here. It can't come here because B should be before the C. I hope this point is clear. So now how are we going to go about? See carefully. Now coming to this, if I fix B here, let us go one by one. If I fix B here, so only one. Now CD. So now see carefully. C, D. Any one of the 2 cities she can visit. As soon as she visits, let's suppose D. Now only one place C. That is 1. So here C is there. Okay. Now you see AB. If I just go for fundamental principle of counting, 1 into 1 into 2 into 1, answer is 2. Now just see, we have fixed AB. Okay. We have fixed AB. See here, we have already. When we have fixed AB, there are 2 possibilities. See, AB, correct? One possibility here, one more possibility here. Without letting you can get. Now one more case. Here, what we, dear students, now let us move on to case 2. Now in the case 1, what we have did? A in the first position, B is in the second position. Again fixing A in the first position only. A is in the first position for a while. A is in the first position. Now just suppose that B is here. Okay. Now see, B is I am fixing. 1 means only one element. Now I have got choices with what? B means C. I mean to say C and D. But they said B should be before C. Because of this, C should be surely here. So only one object can be thought of filling. Now surely what should happen? D will be here. So 1 into 1 into 1. What's the answer? 1. You just see A, then D, B, C. That's what you have got. A, D, B, C. Only 1. Last case. What? We have fixed A in the firstmost position. Case 3. See? Yeah, surely for this, no, thinking capacity is required. So see here, A. As soon as I wrote A here, surely only one object. Now A before B and B should be before C. So nothing but after A, B should come and after B, C should come. And you can see here, yeah, here it used to be B and here it is C. Nothing but one object. Surely D should come here. So DABC. That's what you got, DABC. So totally how many cases? 3 cases. Here again, here by fundamental principle of counting, 1 into 1 into 1 into 1 is 1. Total this. Again by fundamental principle of counting, addition rule, 2 plus 1 plus 1. Answer is 4. That's what we got here after this, right? So this is a benefit of which concept? Permutations and combinations. Kindly make a note. Dear students, having completed all the problems from the 3 model question papers, I want to discuss one problem from NCERT, exercise 14.2. Reason behind to take this problem is to make you understand the importance of how the probabilities should be defined. And as soon we see this, there is no need to solve for you and then know the answer. We can understand from the logic. See, if we recall the Venn diagram, see carefully, this is our event A and this is our event B and this is the sample space. And this region, whichever is present here, this is our A intersection B. So from the diagram is very clear that this part is smallest of AB. So nothing but A intersection B is a subset of A as well as B. For A also it is subset and for B also is subset. We are not talking about anything about A, B. It should be given the question whether A is subset of B or B subset of A. So we have just given a comma. But both this set A, B, nothing but this set A, this entire set B should be, it is contained in A union B. And depending on the problem, it can be equal also. Now, when we have understood this, this also implies that if I take probability of A intersection B, this should be strictly less than probability of A, or for probability of B, and it should be strictly less than probability of A union B. Understand, when I have taken P, nothing but a numerical value, so less than symbol has come. This is anyway a set type, so it is subset. Now come here, they are asking whether it is properly defined or not. See the intersection value. This value should be least of all. But if you see, P of A is, since P of A is equal to 0.5 is less than the value of P of A intersection B, whose value is what? 0.6. Hence, it is inconsistent. It is not defined properly. That's what in one of the model paper we got negative value. Okay. Now, no sir, I want to understand sin more clearly. No problem. Find P of A union B. You'll come to know yourself. Probability of A union B will be what? Probability of A plus probability of B minus probability of A intersection B. What is the value of probability of A? 0.5. For probability of B, it is 0.7. And for this, it is 0.6. Subtraction of this will be 0.1, 0.6. Now you compare this value. And you see, union itself, the largest of all, is less than P of B, which is 0.7. Why this happened? Because it is inconsistently defined. I am saying there is no need for us to work this much. As soon as we understand this logic, and we know that intersection value should be, probability of intersection should be less than the probability of A or B. For both, it should be less, and it can be less than union. I will do one thing, I will use the word and here. You may think that anyone, it should be both. For both, it should be. Okay. Now come here. If you just see this, both of this value is less than P of A union B. Obeying this, therefore it is consistently defined. No sir, I want to check it. What will be probability of A union B formula? It is equal to P of A plus P of B minus P of A intersection B. A union B probability is 0.8. This will be 0.5, 0.4 minus P of A intersection B. So transpose this one here and this one here. We get probability of A intersection B is equal to, this value is what? 0.9 minus 0.8. As soon as I transpose, I'll get 0.1, and this 0.1 is less of all the values. That's what. Okay. Method solving is, we have said already that it is consistently defined. Make a note. Dear students, with this we come to end for this chapter, probability. Do well, study well, give you 100%, all the very best, study well, and God bless you all. Do like, share, subscribe to our YouTube channel, Math Universe with Dr. Naseer Ahmed. Thank you.